All right, good morning, everybody. Please feel free to ask questions if you want, but speak loud. I'm not sure how high the speakers are. They might have got turned down last night. Today we want to finish graphs of the trigonometric functions. And just to remind you, we have 3 of them that you really should memorize. We have the sine function. Boy, bad pens in here. The sine function looked like this. It went between plus and minus 1. And it had period 2 pi. So it crossed the axis at 0, 2 pi, minus 2 pi, and so on, every multiple of 2 pi. Touched the axis every multiple of pi. Right? It also crossed halfway in between. And we had the graph of cosine, which was exactly the same shape, but it started at the top of the wave. So it looked like this. And 2 pi units, it was back at the top of the wave. Both these continue on forever in both directions. Now, finally, we said we could plot some points and use some graphing properties to figure out what tangent looked like, right? Or we could just plot lots of points. But tangent had an interesting graph that looked about like this. In calculus, you can show that this actually crosses the origin here at a 45-degree angle. So it's just tangent to the line y equals x if you want to know how steep to graph that. You have to have calculus to show it, though. But this is the graph of y equals tangent x. And we said we could sketch that by putting an asymptote at x equals pi over 2, x equals minus pi over 2, and say it is pi periodic instead of 2 pi periodic. So it repeats every pi unit. The asymptotes occur at odd multiples of pi over 2, and it crosses the x-axis at whole multiples of pi over 2, at whole multiples of pi. So it looks like this, repeating every pi unit. If you want to know how steep to graph it, here's a nice easy point halfway between this crossing point and the asymptote. Well, it's at 0 and pi over 2. This must be pi over 4 halfway in between. It's exactly 1 unit up because remember, tangent of pi over 4 is 1. And by symmetry, you can say this point over here is then minus pi over 4 minus 1. There's how to graph y equals tangent x. Now the question becomes how to graph the rest of the trig functions, right? And these will go much faster. However, the first 3 here are the important ones. These are the ones you have to have memorized. They come up a lot. The remaining 3 you'll see once in a while in calculus and higher courses, but not nearly as much. Here's how you can get the cotangent function. The nice thing is they come in pairs, just like sine and cosine are exactly the same shape. You just have to slide this one over, or slide this one over pi over 2 units to get this one. Similarly, the tangent and the cotangent will be the same shape, except you have to flip the tangent upside down and slide it over. And the secant and the cosecant will be the same shape. You just have to slide them over. So in some sense, you only have to memorize 3 graphs and figure out how to move them around. Here's how you can get cotangent. So we'll say this, to sketch, I'm going to put it here. Y equals cotangent x. You do this. You use that, the cofunction identity says the cotangent of x is tangent of 90 degrees minus x. Well, write it in radians, it's pi over 2 minus x. So there's the cofunction identity. rather than plotting a lot of points, this is real insightful because we want to be able to do graphs just like this shortly. And then, remember, tangent's an odd function. If you take tangent of minus theta, the minus comes out as minus the tangent of plus theta, right? That's the odd property. I'm going to use that step now and say if I take minus this angle, calling this theta, if I take minus this angle, I have to cancel it with the minus out here. So this minus can come in and reverse these, put them back that way. Now I know exactly how to graph cotangent just by using the odd property and the cofunction identity from tangent. Because after all, this is an A equals minus 1. B equals 1, whatever multiplies x. C is whatever is subtracted here is pi over 2. And D is 0, I'm not adding anything. Graph y equals A tangent bx minus C plus D. I can sketch those, right? All I have to do is do a shift by C over D, I'm sorry, C over B, D, just like the other graphs, because it's the same graphing technique from algebra, right? So the letters act exactly the same way on any function, including all of the trig functions here. Well, C over B is pi over 2 over 1, so it's pi over 2. D is 0. So what it does is it takes the tangent graph and moves it pi over 2 along the axis in the horizontal direction, nothing in the vertical direction. I take this one that used to go through the origin, and instead of going through this very important point, maybe I should mark it here, 0, 0. Well, these are the 3 important points for tangent. You move it over to pi over 2, 0, right? That's the shift. Well, was the origin comes here to graph this. Now there's one more thing, there's a minus, so there's a flip upside down. That's actually it, right? Because the stretching factor A is 1. There's no stretch. All right, we'll say stretch equals absolute value of 1 is 1. That's the identity stretch, doesn't change it. The period is 2 pi over B, but B is 1. I'm sorry, pi over B. Tangent period was pi, and so so the period when you put a B in here is pi over B. We said is pi now. So it has the same period as tangent. It's not stretched horizontally, and there's no stretch. All you do is take this graph, slide it over pi over 2, and flip it upside down. There's nothing more to it than that. Well, that means the asymptotes move over pi over 2. Instead of being a pi over 2, it's now pi. Instead of being a minus pi over 2, it's now 0. There are the asymptotes. Instead of going like this, it flips upside down and goes like that. That's it. To sketch the cotangent, you slide the tangent graph over pi over 2 and flip it upside down. So what was an asymptote here is now where it goes through, and it goes down like this instead of like this. This is y equals cotangent x, and because its period is pi, just like tangent, it repeats this over and over. And that, oops, better stretch it out a little more than that. And now you notice the difference between tangent and cotangent. It crosses the axis at odd multiples of pi over 2. And the asymptotes are at whole multiples of pi. So tangent, the asymptotes are at odd multiples of pi over 2, and it crosses at whole multiples of pi. But the cotangent, the asymptotes are at whole multiples of pi, and it crosses at odd multiples of pi over 2, so it just reverses. Then it's flipped upside down. There's the cotangent graph, and now you can graph any A cotangent bx minus c plus d just by shifting and stretching this one. Any questions on that one? So there's 4 of them. let's see if we can't sketch the most general case, because hardly ever do you need to sketch precisely the cotangent. Instead, you might sketch one of these. Y equals a cotangent, dx minus c plus d. You do exactly the same things you did with the tangent function, the tangent function, the sine, and the cosine. You have a vertical shift, a vertical stretch. All right, let me put the shift first, just put the right order. There's a shift point, c over b in x and d in y, just like it was with the sine, cosine, and tangent. Right? Then there's a vertical stretch. For the sine and cosine, we call it the amplitude, but remember for the tangent, we just call it a vertical stretch because it's not a wave. So the vertical stretch factor is absolute value of a, just like sine, cosine, and tangent. Then there's a period, and it's the natural period of the function divided by b. And so the period here, since cotangent has period pi, as we see, its stretch period is pi over b. So this is different than sine and cosine. They have period 2 pi over b, but tangent and cotangent have period pi over b. That's the one big difference. And then finally, you flip if a is less than 0, just like all the other graphs. So now we can graph any cotangent function in this form. In fact, we just did one here with tangent that's completely analogous, but let's do one with cotangent. Suppose I take a sketch y equals 3 cotangent pi over 3x minus pi over 6. What is that going to look like? You can do this on your calculator actually, but it won't show you the exact points in general. Sometimes you can guess them if it's an easy graph like this one, but generally you can't guess the points. I want you to be able to find exact points for the asymptotes. I want you to plot the asymptotes on these. Those are very important. People look for those. So we say here is a cotangent, bx minus c, and there's nothing on the end, so I got d equals 0. This is typically the case with everything but the sine and cosine. You seldom have a vertical shift in applications on the other ones, although you can certainly do it. Now, I do those 4 things. They're sort of 5 because this has 2 in the first one. The shift point is c over b. Pi over 6 is what's subtracted here, not what's added. Over b, pi over 3. And d, 0. Well, the pi's cancel because they're both numerators. And it's top times bottom, 3 times 1, over middle times middle. 6 times 1 is 3 over 6. 0 is a half 0. So we're going to take this graph and the cotangent 0 point used to be on an asymptote. Now there's going to be an asymptote at 1/2. So we're going to take this graph and we're going to shift it and stretch it. And here will be the graph of the result then. Instead of drawing the asymptote at 0, I'll draw it at x equals a half. And now, this is my shift point, if you will. What used to be the origin will now be here. Then there's a vertical stretch, absolute value of a, which is 3. There's a period for the cotangent, it's pi over b. So it's pi over 3. I'm going to be careful on this one, right? Pi on the top is pi over 1. Now these are both numerators, the pi's cancel, and you've got top times bottom is 3 over middle times middle is 1. This just comes out to be period 3. Finally, we say there's no flip because a is positive. I can graph it exactly now, right? I have one asymptote because of the shift point. The period is 3, so I just move over 3 units and draw another one of these. I need some more room. So I'm taking this graph and sliding it over and stretching it, right? So I'm going to have another asymptote 3 units later at 7 halves, right? 1/2 and 3 is 7 halves. Then it's going to cross halfway in between. Halfway between 1/2 and 7 halves is 4 halves, right? Halfway between 1 and 7 is 4. So 4 halves or 2. And then it's this shape, it goes down through here, so I'm going to draw it like this. There's one period of the cotangent. It's as easy as that. Find the shift point, put an asymptote through it. Go one period over, put another asymptote. Put the graph going down through the point halfway in between if it's unflipped, or up through the point halfway in between if it's flipped. I'll probably give you full credit for that, but to really say that you've got it accurate, you want to say, well, maybe it's supposed to be stretched way up like this or real flat like this because it's flattened. How much is the stretch in between? Well, now you go to the vertical stretch. The vertical stretch factor is 3. And remember, if there's no stretch, this point halfway in between, in this case, halfway between 1/2 and 4 halves, you can average those 2 points. 1/2 plus 4 halves, write it that way, over 2. Let's say it's 5 halves over 2, it's 5/4. So halfway in between here is 5/4. And at that point, it would normally be a 1, right? If it was unstretched. But our stretch factor is 3, so how do I fix it? I can make it 3 times as tall, or I can just rescale the axes and call this 3. That's what I like to do. Then you just draw the same shape over and over and relabel the axes so they're scaled differently. And similarly here, halfway between this one and this one, let's see, I need to add 3/4 to this one. This must be 11/4. I go down to -3 by symmetry, if you like. So there's a real nice accurate graph of y equals cotangent, y equals 3. You know, I wrote cosine. Nobody said anything. Tell me on that. This is supposed to be cotangent. I didn't notice I wrote cosine. 3 cotangent pi over 3x minus pi over 6. And you notice an interesting thing. When B or C and C are both in units of multiples of pi, then what you get on the axes is these things come out at nice fractions instead of having pi in them. Right? If you just make B and C numbers without pi, then you get pi in the asymptotes and crossing points. But if you put pi in here, then those go away and you get nice fractions for these cross. All right, so there's the graph of one of the cotangent functions. Any questions on that one? All right, the last two. In some sense, these can be the hardest two because they're reciprocals. How do you graph reciprocals? They're actually not the hardest two. They're pretty easy to graph. I'm going to give you a big hint that'll make these really easy. Right? To sketch, similarly, the fifth graph here, y equals secant x. How can I do that? Just use the reciprocal, 1 over that is, the cosine function, right? Because after all, secant of x is 1 over cosine x. We can figure out what it looks like. Let's graph the cosine function. It looked like this. Repeated every 2 pi units. Went up to 1 and down to -1. So how do we graph its reciprocal? This is kind of easy here, I hope you'll see. When the cosine is equal to 1, what is the secant? The secant is then 1 over 1 is also 1. So we have this point here, right? Now let's see at this point over here maybe. At pi over 3, right? It crosses at pi over 2, but at pi over 3, remember the cosine is equal to a half. If the cosine is a half, what's the secant? 1 over a half is 2. So at pi over 3, this is actually equal to 2. And at pi over 2, where the cosine is 0, well, secant should be 1 over 0. That's undefined. There I have an asymptote. Where the cosine crosses, you get a division by 0, and secant has an asymptote everywhere. So every crossing of the cosine, you just draw an asymptote. Where the cosine is equal to 1, the secant is equal to 1, so you just put a dot for the secant there too. And then you notice the secant, as cosine gets smaller and smaller y values here, the cosine being 1 over those y values, like when secant is a tenth here, or cosine is a tenth, the secant will be 10. When cosine is 1/100th unit up, secant will be 100. This will go up higher and higher, approaching this asymptote. So you get this behavior. It looks like that. It's a U-shaped up thing because it's 1 over this thing. All right? When the cosine is 1, it's 1. When the cosine is a half, it's 2. When the cosine is a tenth, it's 10. And so on. And same thing over here. And now here, when the cosine is minus 1, secant is 1 over minus 1 is also minus 1. Here at 2 pi over 3, let's say. Remember what cosine of 2 pi over 3 is? You can figure it on the unit circle. It's minus a half. I draw this right. Which means secant is minus 2. And it looks like this thing flipped upside down. By symmetry, it's just this one upside down because this is this part of the cosine upside down. It looks exactly the same shape, a U shape down. So U shape up, U shape down, and then it repeats. U shape up, U shape down. There's what the secant looks like. It just touches the peaks and valleys of the cosine function. Here is the natural secant function. It kisses the cosine function at all multiples of pi, right? This is pi here. 0, pi, 2 pi, 3 pi. It just touches the cosine function at each of those peaks and valleys. And where cosine is 0, it has an asymptote. It has to approach the asymptote. It's just as easy to draw as that. You notice that its period is equal to 2 pi because the cosine's period is 2 pi, right? So maybe we should write out some of these properties. It has asymptotes. You better notice another color. It's not real dark, is it? So period 2 pi. The asymptotes are, let's see, pi over 2, 3 pi over 2, 5 pi over 2. Oh, it's odd multiples of pi over 2 again. And it just touches the peaks and valleys of the cosine function. Now, how about the secant of the cosecant function? If we can draw the secant like that, we can figure out what the cosecant looks like quickly, right? Because the sine function is exactly the same shape as the cosine function. When you take its reciprocal, it ought to be exactly the same shape as the secant. So the last one is the cosecant x. What I do for that one is I just take the sine function, which is also a sine wave. We said we call both sine and cosine functions sine waves because they're exactly the same shape, just shifted over. There's y equals sine x. I can figure out immediately how to graph cosecant because it's that one just slid over pi over 2 units. So wherever this one is 0 now, I get an asymptote. And when the cosecant should just touch the peaks and valleys of sine, just in complete analogy to that one. U shape down, sound like Homer Simpson, right? U shape up in hospital bed or whatever. It goes down, it goes up, and we got the hospital. Anyway, so there's the there's y equals cosecant of x is just the reciprocal of sine. When sine gets small, cosecant gets big. Where sine is 0, cosecant has an asymptote. It's exactly the same shape as the secant, just shifted over. We could use one of those cofunction identities to prove it, actually. It's quite easy. It's exactly the cosecant function. Slide it over 90 degrees, pi over 2 units. If you just take this one, slide it over, so the asymptotes are at whole multiples of pi and the peaks and valleys are at odd multiples of pi over 2, then you get this one. There's nothing more to it than that. So even though in some sense those should be the hardest, they're really easy. You figure them out immediately from the sine and cosine. Any comments on that one? You're waiting for your test back. I mentioned I haven't got those finished yet. I should have by now. I got caught up with some stuff. So they should be back any day now. Or I don't have those back yet. Let's look at an example because now we can sketch a secant bx minus c plus d or a cosecant bx minus c plus d. Suppose I asked you to sketch y equals 2 secant 2x minus pi over 4 plus 1, let's say. What if I had to sketch that one? You do the same trick, except now it touches the peak and valleys of the corresponding reciprocal function. To sketch this, first sketch, this is a two-step method. If you do a two-step dance, you can do a two-step thing here. First step is to sketch the corresponding reciprocal function. Draw, sketch y equals to cosine 2x minus pi over 4 plus 1. Exactly the same thing, just with secant replaced by cosine. I know exactly how to do this because we already did these, right? Here's a equals 2, b equals 2, c equals plus pi over 4 with subtracted, and d equals 1. So I take my shift point, c over b, pi over 4 over 2, d, 1. And I say, now these reinforce, right? Think of 2 as 2 over 1. It's top times bottom over middle times middle. It's pi over 8, 1. And so I'm going to move what would have been the origin over to pi over 8, 1. So that's 1. Then the amplitude, because we're doing cosine here, is absolute value of 2 is 2. The period is 2 pi over b is 2 pi over 2 is pi. So what I'll do is, since it's amplitude 2, I go up 2 units. This doesn't look 1 unit up, does it? Let's put it a little higher. Suppose that's pi over 8, 1. I go up 2 more units and down 2 more units and draw the asymptotes. Remember how to draw these? So you put the midline through the shift point, drawing cosine, and then this is 2 units up and 2 units down because the amplitude is 2. Since the cosine is unflipped, put that down for the 4th step. You start at the top wave, right? To sketch a cosine, you start above the shift point at the top. You go over 1 period, which is pi. So you go from pi over 8, you add pi. Now you've got 9 pi over 8, right? Pi plus pi over 8 is 8 pi over 8 plus pi over 8 is 9 pi over 8. And you sketch the same point that you had here. So if you started at pi over 8, 3, the top guideline, this will be 1 period over 9 pi over 8, 3. This seems hard. It's just sketching cosine. We did these, hopefully you remember. So we started here and we finished 1 period here, starting from the top, going down to the bottom, like that. And then I just have to repeat that over and over, and I've got cosine. You say, oh, that's just cosine. How am I going to do secant? You've pretty much already got it, because to sketch the secant, you just first draw the corresponding cosine with the same numbers. Then you sketch the secant to just touch the peaks and valleys of the cosine and put asymptotes wherever the cosine crossed its midline. So 2 sketch the secant with the same numbers to touch the peaks and valleys and have asymptotes where it crosses the midline. The line through the middle. So here's an asymptote right here. Here's an asymptote right here. Asymptote here, wherever the cosine crosses this midline. And then I sketch the cosecant. U shape up, shape down, between the asymptotes. U up, U down, between the asymptotes. And here is y equals the corresponding secant, same letters. 2 secant, 2x minus pi over 4. And that's all you have to do to sketch secant and cosecant. You just sketch the corresponding cosine or sine and touch the peaks and valleys. Make sure the asymptotes at the where it crosses the midline. But even though they seem hard, once you realize that, it's pretty easy. You want to do one more? Is that good? Anybody? We can do more if anybody wants. All right, well, I expect you to try all those out. Problems, this is out of section 6.2, and now I'd like you to finish 1 through 5. Make sure you do problems. There's parts on those. So it's not like it's only 5 easy problems. I think they finally got the heater turned on in here. Let me get this off. All right. And that's the end of the graphs. As I said before, these are used in all sorts of wave analysis and so forth, so they're really useful. And the next topic then for the rest of the period is to look at inverse trig functions. We've mentioned these briefly in solving triangles. Now we want to discuss them much more generally. This goes back to algebra, unfortunately. And all those things in algebra said, why do we need this? You don't find out until you get trig in trouble in other classes. You have to say from algebra, what is an inverse function in general? We won't get through this today, but we'll get it started. It's kind of complicated, but you have to understand the algebra to know what you're doing. Rote memorization of this is like trying to rote memorize the first 2,000 digits of pi or something. You know, how do I rote memorize that? Very few people can do that. But if there happened to be a pattern in it, all right, if it was like 1/6, so it repeated every so many digits, then you can memorize the pattern and get it, right? That's what we're going to try and do here. We're going to try and learn the tricks from algebra for graphing inverse trig functions. And then if you memorize the tricks, it's like having a pattern in a decimal. You can figure out how to do this quickly. So from algebra, recall that the inverse of a function works like this. A function is said to be 1-to-1. Sometimes written for brevity as this, 1-1. If, whenever, this is very abstract here, but it has a real obvious meaning. If whenever y2 equals f of x and y1 equals f of x, for some value of x, it follows then that y2 equals y1. What does that mean? I have to really think about it. It means that each y value corresponds to only one x value. If I have a graph like this is not one-to-one. All right? Because I can take this value right here and say, here's a function. I should put this the other way. I'm sorry. If y2 equals f of x1, y2 x2, and y1 equals f of x1, it follows that x2 equals x1. I'm not writing that right. Gosh, I know how to write this better than this by now. If a certain y value is f of x2 and that same y value is f of x1, I just put these on the wrong ones. Then it follows that x2 equals x1. Sorry about that. It means this graph, which is the way I should remember it. All right, sorry about that. If at x2 you get a certain y value y, and at x1 you get the same value y, 1-to-1 means it has the x values have to be the same, but here they're not. So this one is not 1-to-1. However, this function, y equals f of x, is 1-to-1. If I take any y value whatsoever, say from this value x1, there's no other y value that comes from any other x value. This is the only x value that can give me that y. Right? And what this amounts to is passing a horizontal line test. It means graphically that no horizontal line can intersect the graph more than once. So this is the way you define it so you prove things. That's why it's clumsy to remember. If y equals f of x2 and y equals f of x1, it follows for the same y, it follows that x2 equals x1. You can prove things with that, but no horizontal line intersects more than once is the way to think of it easily. Remember, a function is a graph that no vertical line intersects more than once. If on a function no horizontal line intersects more than once, then it's a 1-to-1 function. So a 1-to-1 function, no horizontal or vertical line intersects more than once. So that's the trick. Among functions, graphs where no vertical line intersects more than once, we restrict to those that no horizontal line intersects more than once. Now, the 1-to-1 functions are nice because they're invertible. You did this in algebra. I don't know if you remember it. But the idea is, if you give me a y value, I can give back the x value. I undo what the function does. Because there's only one x value that goes with it. But if I have a function that's not 1-to-1, you give me the y value, I can't tell you which x value it is. So that's the idea. A 1-to-1 function is invertible. Because if you give me y, I can tell you what x was. Now, how can we do it? It actually works like this. Here is a 1-to-1 function, let's say. How do I know that's 1-to-1? Because no horizontal line intersects more than once, right? Here's y equals f of x. What should be the inverse function? The function that when I give you y, you give me back x. Well, it's this function. If I take any point on here, a, b, it has to have the reverse pair be a. All right, so that if you give me y, plug it into this function, and get back x, right? B being y and a being x. Well, if you look in the plane, AB and BA, how are they related? Since you're just interchanging the x and y coordinates, it's equivalent to flipping over this line y equals x, right? You flip the line y equals x, it interchanges the x and y axes. And the graph of the function that undoes this point AB to give you BA, then comes out to be, since you just flip the axes, exactly the same shape as the original function, just turned the other way. So if this is y equals f of x, this is now x equals f of y, interchanging x and y to get the inverse relation. And if the function is 1-to-1, because this passed a horizontal line test, no horizontal line intersection once, when you flip it, this one will pass the vertical line test, no vertical line intersection once, so it'll be a function. Y can be a function of x. So we also say that whatever function of x, y is, we call this the inverse function. That's the idea. If you give me B, I can tell you what A came from, and I plug it into this function that we call the inverse function. We know it's a function because no vertical line intersects the one once, because no horizontal line intersects the first one. That's how inverse functions work in algebra. It's kind of complicated, but it really makes sense if you think about it. When you want to undo a function, all you have to do is flip it over the line y equals x, then you can plug in y and get back x, right? Or the original function. So here this graph shows the inverse function as the, let's call it y equals f inverse of x, that undoes the original function, as the flip, if you will, of y equals f of x over the line y equals x, so that the x and y coordinates are interchanged. That'll be the inverse function. Now what happens is this wonderful property. This is for general functions, not just trig functions. If I take the function f inverse of f of x, what is it going to be? Let's say a. And any number a and put it in the original function f, any a for which is defined, right? What is f inverse of f of a? Boy, this is better. Well, in the graph, if I put in a, b as a point on the graph of f of x, I put in a, I get back b, right? So this will be f inverse of b. But the definition of f inverse is that if b is in there, it gives you back a. F inverse of f of a just gives you a back. The inverse function undoes what the original function does. If you put a into f, f inverse gets you a back. And, my symbol for and, if you take f of f inverse of b for any b for which f inverse is defined, f inverse of b gives you a. This is f of a. And then f of a is b. So it's b. F also is the inverse of f inverse. So they're inverses of each other. We can call that equation 1. That's the idea of an inverse function. It undoes this function. If you put in x into the one function, f inverse gives you x back, right? It undoes the y coordinate, gives you back x. Y coordinate b gives you back x. But also then as a benefit, the original function undoes your inverse function. You put b into the inverse function, f gets you back to b. All right. So that's inverse functions in generality, just for an example from algebra. All right. Suppose I took y equals x squared. Easy parabola, right? What about the inverse function for that one? It doesn't have one. Why does this not have an inverse function? It's not one-to-one, right? But you didn't expect to get an algebra lecture today, huh? If I take this horizontal line, if any horizontal line intersects it more than once, this function is not one-to-one. It is a function because it passes the vertical line test. No vertical line intersects it more than once. But it's not a one-to-one function because the horizontal line intersects it. Because of that, I can't invert it. I can't get it. The inverse, if I flip it, will look like this and it won't be a function. That's why we have to have one-to-one. Right? A vertical line will intersect one to one. So this is not one-to-one, no inverse function. We flip it over the line y equals x, we call it an inverse relation, and it's not a function. What am I to do? How do I find an inverse of the square function? I know it exists, right? I ought to be able to undo a square. Here's how you do it. Instead, consider half of the square function. Let's just consider the square function for a non-negative number, half of the parabola. This will still be y equals x squared, but restricted to x non-negative. Now it's half of a parabola. Starts here at the point 0, 0. If you put in 1 and square 1, you get 1, so it goes through 1, 1. It also goes through 2, 4, and all these other wonderful points. It keeps going up. Notice no horizontal line intersects more than once. This is one-to-one. I can inverse it. What's the inverse? Well, I flip it over the line y equals x to see what it is. And maybe you remember computing these inverse functions from algebra, right? To inverse it, to inverse y equals x squared. This is what you did in algebra. We won't need this so much this semester. You interchange x and y. That corresponds to the flips. You write, so if it's y equals f of x, you rewrite it as x equals f of y. So you write x equals y squared. Right, x equals f of y instead of y equals f of x, and solve for y. That's how you found inverses. Maybe that looks familiar. Well, I can square root both sides, and I get y equals plus or minus square root x, right? That was the first one we had. The reason I don't get one plus or minus is one of them is that I didn't start with a one-to-one function. If I also restrict this to x greater than or equal to 0, this is what I did, then this one will be restricted to y greater than or equal to 0, which means you only get the plus sign. Oh, obviously, the inverse of the square is the square root, right? So it looks like this. You've probably seen it before, right? Y equals square root of x is the inverse of the square function. You give me a square, I can square root it and give you back the original number. That's the idea of an inverse function. It undoes the original function. But what I had to do was restrict to x greater than or equal to 0 to make it invertible. If I allow negative numbers, I don't know whether to put square root of x or minus square root of x, right? So I can inverse this one, the square root, when I know I came from a non-negative number, but not this one if it might have come from either positive or negative. I don't know which one to pick. And then, you see what happened here, right? Here's the line y equals x. To get the square root graph, I can just take the square graph, which looks like this, flip it over the line y equals x, and the square root function is exactly half a parabola, right? The half parabola y equals x squared restricted to x greater than or equal to 0, flip became the square root, so it's exactly the same shape. The square root function is actually half of a parabola. It gets like that, and then it goes through these same points. That went through 0, 0, you reverse the coordinates, you get 0, 0. That one went through 1, 1, you reverse the coordinates, you get 1, 1. That one went through 2, 4. This one, the reverse coordinates has to go through 4, 2, right? The square root of 4 is 2. And so on, 9, 3. And so all you do is you reverse the coordinate pairs on this one to get the coordinate pairs on its inverse, the square root. Right? So there's the review of algebra that everybody forgets. We have to do it or nobody can understand the following part. Now we want to do the same function, sine function. Seems like that clock is dragging too slow. We need a break here, don't we? Is this a lot of stuff? I'm not getting much input today.
It is quite a bit, but I think I'm tracking everything.
Okay, good. All right, let's try this one then. Now, apply this theory to the function y equals the sine of x. We have exactly the same kind of problem we did with the square function. When we draw the sine function, it's a wave like this. This is really even worse than the square function because not only is it not one-to-one, if you put a horizontal line through here, it's intersected an infinite number of times. So if you tell me what the sine of x is, there's an infinite number of answers that might have gotten that sign, right? Might be this x, might be this x, might be this one, might be this one. That's because this thing repeats over and over. So here's y equals sine x. And just like we made the comment over there, this is not one-to-one. We can't, since the horizontal line intersects it more than once, we can't say which x it came from. So we're going to do what we did here. I call this Howell's rule. Everybody see, here's a good break. Gilligan's Island is a 50-year-old black and white, well, started black and white, finished in color TV series, and there was this famously rich guy, Mr. Howell, who always gets his way. And one of the episodes, something he wants to make fit doesn't fit. He says, it doesn't fit. Break off a piece and make it fit. He always has to have his way, right? So that's what we're going to do here. It's not one-to-one. We'll break off a piece and make it one-to-one. We'll do the same thing here, right? So now, consider just the piece of sine x, y equals sine x only for x between minus pi over 2 and pi over 2, doing it in radians. So it's between plus and minus 90 degrees, if you like degrees. What does that look like? This was minus pi over 2 here, right? Where sine was minus 1. And this is pi over 2 here, where sine was equal to 1. So if we just take this piece, lo and behold, it's one-to-one. No horizontal line intersects with this piece more than once, just like on the parabola. No horizontal line intersected that piece more than once. So I can take this piece and flip this over the line y equals x to get its inverse. And so I look at that piece there for a second and I say, wait a minute. All I have to do to get the graph is like I did with the parabola. I reverse all the coordinate pairs. 2, 4 becomes 4, 2, right? And so here I have these 3 points, for instance. I can do more points, right? But sine has 0, 0. So the inverse function, when I flip it, is going to have 0, 0. And this point here was pi over 2, 1. So I'm going to have the point 1 pi over 2. Reversing the pairs. You know, if you wrote memorize this, you'd never be able to remember all this, right? But if you figure out, oh yeah, I'm just flipping it, then you can do it. Minus pi over 2 minus 1 is this point. So over here, I have to have minus 1 minus pi over 2. So here's Howell's rule for the sine function: is break off a piece and make it one-to-one. All right. And if you graph the rest of it, it has to be exactly the same as this, right? Because we're just flipping it over the line y equals x, which looks about like that. And it'll be the same shape, just turned this way so that it goes, so the x coordinates is going minus pi over 2 to pi over 2. The y coordinates go minus pi over 2 to pi over 2. And so the y coordinates going from minus 1 to 1, the x coordinates go from minus 1 to 1. That's the inverse function. What should we call that? Since we inverted the sine function, we'll just call it the inverse sine function. Y equals inverse sine x. That's what we call it. Or arc sine is the other name. This one is more suggestive. But it was like this. We said for general functions in algebra, if you get y equals f of x, and flip it over the line y equals x, you get some curve that looks like this. Y equals, and we called it f inverse of x. This notation does not mean 1 over f of x, right? It means we interchange the x and y coordinates here, so that if this was AB, this was BA, and each point is just reflection straight across the line y equals x, same distance the other side. So this is how the f inverse, and it's a conflict of notation. If I write 2 inverse, I mean the multiplicative inverse, I mean 1/2. But if I write f inverse of x, I do not mean 1 over f of x. I mean this function I got by flipping. So don't let that notation throw you. Because otherwise what you'll do is you see arc sine, oh, that's 1 over sine, that's just the cosecant, right? Wrong, it is not the cosecant function, it's this one. We just saw cosecant, right? It looks like U shape up, U shape down. That's 1 over the sine. This is not 1 over the sine. It's just a conflict of notation. If you put this on a number, it means 1 over the number, but if you put it on a function, it means the inverse function by flipping. Unfortunate conflict of notation, right? You just have to know, is it a function or is it a number, and then know what to do. Any questions on that? All right. This is where we should normally quit. I really love 50-minute classes because you can just hang on to it and go study it. Hour and a quarter, that last 45 minutes, sometimes I have to get out the joke book or something. I don't know. All right. So there is what we call the inverse sine function. How do we get it? Similar to how we got the square root function. We take the sine function is not 1-to-1. It doesn't have an inverse. It's a function. If you flip it on the line y equals x, it looks like this. It snakes up here, right? That's the flip. To have the flip be a function, you have to take a piece of it where there's no horizontal line intersects more than once. And convention says you pick this piece. And when you flip it, you get this, and we'll call it the inverse sine or arc sine. You can fill in more points on here if you want, right? What about this? If I go to the point halfway in between here, pi over 4. We know what the sine of pi over 4 is, right? Sine of pi over 4 was square root 2 over 2, we remember, from the 45, 49, 90 triangle, right? So we know this point is on the graph. If this point is on this graph, then this one has another point with those reversed, square root 2 over 2, pi over 4. So you can find more points on here too. There's a minus square root 2 over 2 minus pi over 4 also. All those special triangles that got points on this curve can now be reversed. Those points can be reversed to find points on that curve. All right. Properties. Since it's an inverse function, guess what? It undoes the sine if it comes from this piece of the sine. This is why you can't just do remote memorization, I think. If you take, by property 1, if you take the inverse sine of the sine of x, any sine of theta, let's say, what should you get back? Actually, let's use x because I used x up there. X will be the angle. What should I get back? Equation 1 said if you take f inverse of f of x for any function, you get back x, right? It undoes the f. So inverse sine of x just gives you back x. Except there's a problem. Why would this be different than this? The problem is that the sine function wasn't invertible, only a piece of it was. So it gives you back x if x came from this piece that you inverted, minus pi over 2 to pi over 2. So it works, of course, on the piece that you inverted. But you get something else otherwise, right? We'll talk about what you get there later. There's a nice property. It undoes the sine function for this range of angles. That's very important, probably the most important range because it's close to 0. And also by equation 1, for any inverse function, f of f inverse of x also gives you x back. I guess we called it a here and b here, but you can call it x if you want to. Just a variable, right? So we ought to have, similarly, that the sine of the inverse sine of any number x gives you back what? It ought to give you back x also because f does f inverse. These were equations 1, right? This one gives you this one. Well, and we're kind of luckier here because this whole thing is flipped and gets back all on the sine function, so it always works. So why would we put a second line if it always works? Well, you notice that the inverse sine is only defined for x between -1 and 1, right? That's the only points that are plotted. When we flip that, the y coordinate's going between plus and -1. When we flip it, now the x coordinates go between -1 and 1. You can only put x between -1 and 1 for this to be defined. We call that the domain. The domain, remember, is all x values that you can put in. And then you get undefined otherwise because the thing's out here. There's no point plotted. That shouldn't be surprising, all right? Because what is the inverse sine problem? If I say inverse sine of x, I'm saying what angle has that sine, right? Just like if I use the square root function, I had saying what number has that square, right? Similarly here, I'm saying what number has that sine. Well, if I say what's the inverse sine of 2, there isn't anything that has sine 2 because sine is always a number between plus and -1. So this will be undefined, right? If x isn't between plus and -1, then in this inside thing here, we're asking what has sine equal to 2 or 3 or 10. There isn't anything, so it's just undefined. Right. All right, now we need to do the rest of the period, just a few simple examples. To understand what's going on is important because if you go on in higher mathematics, not only do they inverse sine, there's some things called hyperbolic trig functions. You have to invert the hyperbolic trig functions. There are lots of other functions too. There's the cardinal sine function, and you want to take a piece of that and invert it maybe. Or there's all sorts of things, even in algebra. I just want to point out, we were drawing this picture here. Don't draw this. I don't think this is useful. You can if you want, obviously. I showed this example of y equals f of x and y equals f inverse of x. No horizontal line intersects this more than once, so I can flip it over the line y equals x. AB going to be A. Just left the picture up there, huh? And said, okay, there's the inverse function. That should look familiar, though. What does that look like that you saw in algebra? You already did this inverse stuff in algebra for a purpose in algebra. Suppose this is the curve y equals 2 to the x here, right? Doesn't that look like y equals 2 to the x? That's how you graph it. It looks just like that. It goes through 0, 1, and 1, 2, and 2, 4, and a whole bunch of other points. Right? You put in 2, you get 2 squared is 4. So here's 0, 1, 1, 2. Maybe up here is 2, 4. So on the inverse function, I should get 1, 0, 2, 1, and 4, 2. Just reverse the coordinate pairs. What is this function here? This is just to whet your appetite for this. You don't have to know this. What's the inverse of the exponential function 2 to the x? It's logarithm base 2 of the x. This is how you get the logarithm function. It's the same shape as the 2 to the x function is the log base 2 of x. And what you then have are these properties. 2 to the log base 2 of x is x because they're inverse functions. And log base 2 of 2 to the x equals x because they're inverse functions. So this is f inverse of f of x equals x. This is f of f inverse of x equals x. And it's exactly the same kind of thing. So I drew this picture over here. I just want to point out that you already did this in algebra with the logarithms and exponential functions. The logarithms were precisely the inverse functions to the exponential function. Because like bank interest grows exponentially. It won't be 2 to the x. That's like bank interest doubling every period, right? But maybe if you get interest every year and it's 5%, then it's 1.05 to the x. And then this will be log base 1.05. And now you say, how long will it take me 5% interest to make $1 million? You can go over here, put $1 million and find out how many years, right? That's very, very useful. Find out how many years it takes to double your money or whatever. And that's what logarithms are good for, is inverse functions. Similarly here, we have a lot of times in trigonometry where we don't want to say, what's the sine of the angle? We want to say, what angle has that sine? And so that's the idea of an inverse function. So let me see if I can do some examples now. evaluate each of the inverse sine functions. Evaluate what is the inverse sine of a half. And again, I'm asking the question, what angle has sine equal to a half? With one more restriction, because there's actually an infinite number of answers if I just say what angles have sine equal to half, right? The inverse sine, if you look at it, tells you what angle between minus pi over 2 and pi over 2 has that sine. Right? There's only going to be one angle between minus pi over 2 and pi over 2 with that sign. That's the idea. So when you want to find an inverse sine of a number, you ask yourself what angle theta has, or if you like x, has sine theta equal this number. Leave a little space, because there's an infinite number of answers, but we're restricting. When you put in a number to take the arc sine, it always gives you only the angle between minus pi over 2 and pi over 2 in order to get the function. Now with that, there's only one answer. What angle between plus and minus 90 degrees has sine equal to half? You can do this on the unit circle, right? Sine is the y coordinate, so I put y equal to half. There's only 2 points on the unit circle where y is equal to half, right? Well, I have to have either this terminal ray or this terminal ray. Which one is it? Well, the terminal ray has to have theta between plus and minus 90 degrees, so it has to be in here. It follows that it's not this one, it must be this one. So this must be theta. What is theta? I drop the perpendicular. Since it goes up to 1/2, this side is a half. Since it's a unit circle, this side is 1. Aha! Pythagorean theorem, if I apply it, shows me that this side will be square root 3 over 2. There is only one right triangle with a leg a half and a hypotenuse 1. It has to have the other side square root 3 over 2. We saw that in the beginning of the course. So it's this triangle. I know instantly theta must be 30 degrees, but we're going to try and use radians in this section as much as we can. It's easier in the long run and higher mathematics. Pi over 6, we'll say. There's the answer. Arc sine of 1/2 is pi over 6. You can try this on your calculator. If it has a computer algebra system or some basic approximation thereof, it will tell you this exact answer, pi over 6. If it does decimals, then you look at the decimal and also divide pi over 6 by 6, and you'll find out you get the same number. So there exactly is the inverse sine or arc sine of 1/2. It's pi over 6. To a harder one. Suppose I want to take the arc sine of minus square root 2 over 2. Uh-oh, what's that one? It's the same question. To do the inverse sine, you're going backwards thinking. It's very hard, I know, at first, because ever tried to talk backwards? How hard is that? Say flugel or something backwards. Ooh, something like that. I can't talk backwards quickly, and you can't do these backwards quickly either. You just have to practice them, right? So again, you say this: what theta has this sign? That's the inverse question. You can answer it on the unit circle, but it's not just what theta is. What theta between minus pi over 2 is pi over 2 has that sign. Then there's only one answer. So I'll run to the unit circle again. And as long as this angle is a special angle, I'll be able to figure it out exactly. If not, I'll just have to do it on the calculator. But when I see square root 2 over 2, I remember that comes from a special angle, so I'm confident, right? You see 1/2 square root 2 over 2, 1 minus 1, 0, square root 3 over 2, plus or minus. All those things come from special angles, and the other numbers don't. All right. So I draw the unit circle. And I want to know what angle has theta, has sine theta equal minus square root 2 over 2. Well, sine theta is the y coordinate. Right? So I draw the line y equals minus square root 2 over 2. It's about here, minus 0.7 roughly. Those are all points in the plane that have y coordinate minus square root of 2. We observe, since it's a horizontal line intersecting a circle, there's exactly 2 intersection points. That means there's exactly 2 terminal rays possible, this one, and that's it. All right? One of those 2 terminal rays generates this arcsine. What can the angle be? Well, the arcsine has to be a number between minus 90 degrees and plus 90, minus pi over 2 and plus pi over 2. So, can't be this one, it's in the wrong quadrant. You also can't go around 12 times, right, and come over to one of these. That's too big an angle too. So you have to, it just has to be somewhere in here, and that means this must be theta. That's the only possibility when it's restricted between minus pi over 2 and pi over 2. There's always one answer, because arcsine is a function. We made it so by Howell. So there it is. Always only one answer for arcsine. It is a function, right? Input a number, get out exactly one number. What theta is that? Well, again, I dropped the perpendicular. If this goes down to minus square root 2 over 2, then the length of the side is plus square root 2 over 2. This side is 1 because it's because it's a unit circle. And I started to give the answer away. What kind of triangle is this? Evidently, if one side is square root 2 over 2, one side is, and the hypotenuse is 1. Pythagorean theorem will show you if you take square root of this squared minus this squared, you'll get square root 2 over 2. There is only one right triangle with this leg and this hypotenuse by the Pythagorean theorem. It's going to be this side, this side, this side, and I see immediately that's a 45-degree angle minus because it's clockwise. Evidently, theta equals minus pi over 4 to make that so, right? So the answer, what's the arcsine of minus square root 2 over 2? It's minus pi over 4. There it is. You just have to ask the reverse question and sketch the unit circle. You can do all of these just like that. How about this one? What's the inverse sine of 1? Again, you're asking what angle theta has sine equal 1 with theta between plus and minus 90 degrees. Minus pi over 2 and pi over 2 radians. Draw the unit circle. If now the sine is the y coordinate, right? So where is y equal to 1? Here's the line of all points y equals 1. It's right here. It just touches the unit circle at one point this time. And so there's only one terminal ray. It's this one right here. What angle in standard position has that terminal ray? It's only pi over 2. You can see it immediately. So evidently, arcsine of 1 is pi over 2 immediately. Right? I mean, you could go around rotation and into here, but that's not between minus pi over 2 and pi over 2. It's 2 pi plus pi over 2, right? So there's the answer to that one. You just find it on the unit circle again, but this time there's only one terminal ray to draw. That makes sense? Have to ask questions when they get harder. Okay, here's D. Now, what is the sine of the arcsine? I'm sorry, the sine of the inverse sine or arcsine of 0.2. Wait a minute. To take an inverse sine by hand, not just a calculator approximation, I need a special angle. 0.2 doesn't come from a special angle. How am I going to get this when I can't find the arcsine? I can't find the arcsine as a special angle exact. I can only get a decimal approximation on the calculator. Nonetheless, I can find the sine of the arcsine because, remember, I think I call the equation 2, maybe not. They undo each other, right? We said this, the sine of the inverse sine of x gives you x back if x is between minus pi over 2 and pi over 2, even though you don't know what it's going to give you yet otherwise. It gives you something else in any case. We call this a piecewise definition. It's equal to this piece if x is in this range, this piece if x is in this otherwise. So it doesn't matter that it doesn't come from a special angle. When it's the sine of the arc sine, and this angle is between minus pi over 2 and pi over 2, and it is, right? This is, pi is about 3, so this is like between minus 3 halves and 3 halves roughly, right? This is between minus 3 halves and 3 halves, so you just get back 0.2. I told you to get harder. Look, I got it easier. How about that? All right. How about this one? What's the inverse sine or arc sine? I'm sorry, the sine of the arc sine of 1.1. How about that? How about that one? Oh, they undo each other, right? Sine of the arc sine of 1.1. Wait a minute. You know, I put this backwards. I'm sorry. I wrote this backwards. This is for the other one. This is sine of the arc sine. It gives you back x, or x between minus 1 and 1. And it's undefined otherwise. Sorry about that. It's the wrong one. Sine, it was arc sine of the sine would be the other one. All right, so this one, we'd like to say it's 1.1, but it's not. If you put in a number bigger than 1, you're saying what angle has sine equal 1.1? There isn't one. The sine is always a number between plus and minus 1. This is impossible. That's why this is written up here. So the answer is undefined. So there's taking the sine of the arc sine, and we're out of time. I just realized this clock is 2 minutes slow, isn't it? So I need to get, I gave you the problems on the previous section. Let's stop this one right here, and it's time to get out of here and bring some questions next time, because we're going to do the other inverse trig functions. They're very similar, so it won't be quite as hard. Thank you.